Hello and welcome to TWSS 2023. Welcome back. We're going to give everyone just a minute to log into the webinar and get situated.
And so this effort is our attempt to start adding more complex chemistries into the simulation. So here's a brief outline. I'll just briefly talk about VSim's collision models. I'll then give an overview of global model. I'll discuss how to couple our global model, or how to couple global models into VSim. Then I'll look at some results and finally the conclusion. VSim has several collision models that are currently implemented in the code. One of them is Monte Carlo. They all use Monte Carlo methods. And some of you may or may not be familiar with the two different Monte Carlo methods that are out there. One is called Monte Carlo collision, or MC. In this model, the total energy and momentum is not conserved. And there's also DSMC, which stands for direct simulation Monte Carlo. And in this scheme, the total energy and momentum is conserved. And we have both of those in our code, so you get to choose. MCC tends to be faster and is okay for most applications. And the nice thing about VSim is it's pretty straightforward to switch over to using DSMC if you thought you needed to down the road. And just one tidbit that I often get asked by customers is, should I model my neutral as a fluid or a particle? And my answer is usually, if you care about the evolution and the phase space distribution of the neutrals, then you will need to model those as particles. Okay. In this work, I'm modeling the background neutrals as fluids. The reactions framework is our latest and most developed collision model. And I just thought I'd give a bit of background on the resolution that you'll want to resolve, or the timescales and spatial scales you want to resolve. You're going to need to resolve the highest collision frequency. And that's because of this little equation here. This is highly simplified, but this term right here basically says that the time step needs to be smaller than the collision period to get the physics right. Another spatial resolution you'll need to resolve is the mean free path, and that's because in our algorithm and most algorithms, particles are paired in a cell, and so for two particles to collide and be within a mean free path, the cell size needs to be smaller than the mean free path. Okay, so now I want to talk about a new feature, or a new direction we're headed in developing some examples moving forward and helping customers get set up with more complex chemistry in VSim. So just imagine if you're modeling CCP or an ICP chamber, and the question then is, what do I need to include? What reactions do I need to include? And unfortunately, particle and cell really can't answer that question. The timescales are too slow, and the timescales are too small in PIC to give you that answer. And furthermore, it's really more of an energy balance and particle balance question rather than a kinetics question. So if you happen to know the chemistry to include, then you can put that chemistry into VSim and you can model that. So that's what I'm going to be talking about now, is the global model that we're using and some of the physics behind the global model. Global models perform spatial averages to compute steady state density of each species. And the equations that are being solved are the zeroth moment of the Boltzmann equation, which is the continuity equation. And in this global model, also called the 0D model, the species densities are coupled via the collisional process. And then there are boundaries, even though it's 0D, that they put in, because you have to include sources and sinks from power sources. The simplification is that all spatial derivatives equal to 0. And then there's also a an energy balance equation, which typically is done only for the electrons. In principle, you could put in ion terms as well. The model that we've been using is Quantumol, their QDB model. This is a commercial global model that has a Boltzmann solver. And it's got some inputs. So the inputs are power and gas flow rates. And then you need to input the pressure. And this also assumes cylindrical symmetry, this version of the software. And again, Quantumol solves the 0th moment and the 2nd moment of the Boltzmann equation in the spatially averaged case. And the output is all the reactions that are possible for a given set. Even a simple chemistry set will have hundreds of possible reactions. Complex chemistry set will have thousands of possible reactions. So even hundreds is too many. The next step is to reduce the chemistry, and this is done by removing each species one by one. This is done automatic for you. When you hit the button that says reduce this chemistry set, and then it reduces it for you, and then and under the hood it says, okay, I've removed this atom or the species, and then if nothing much changes according to their threshold, then it takes it out. Quantumol also has a Boltzmann solver to account for non-Maxwellian tails. So it's using rate equations for their equations, which these rate coefficients usually are assumed to be from Maxwellian distributions, but a Boltzmann solver can determine the impact of non-Maxwellian distributions. Okay, so here's just what I did was I took the same chemistry set and I varied the power from 50 watts to 500 watts. And we see 3 orders of magnitude difference in the electron density. So it's really important to get the power right in your setup. So whatever power you're using in this global model, ideally we would mimic in VSim. So that's a capability that we're working on. And this is just for a simple, I say simple, it's actually pretty complex. It's CF4 and argon. That's the mixture that I used. I think it was like, I forget the ratios. It was like 75% argon, 25% CF4. And then here's a plot of that reduction that I was talking about. So this is electron density here. And the full chemistry gives us an electron density of about 3 × 10⁻�XVI. The reduced chemistry is pretty close. And then there's about a factor of 3 difference in the density when I do the Boltzmann correction. So for us, that factor, we're just trying to get with the ballpark, the initial density. So if we're within an order of magnitude, then for us, that's a good starting point. Okay, so the full chemistry set in this example had 40 species and about 1,000 possible reactions. And the reduced chemistry set has 15 species and 112 reactions. So that's a pretty good reduction. It's still a lot for particle and cell code. And so figuring out which reactions to include is still a work in progress. So the output, at this point now I want to talk about inputting the output from Quantumol into VSim. So Quantumol will tell us which species to include, the density of the dominant species, the electron temperature, and the specific reactions to include. So this last bullet point there, that specific reactions, is we're still working on that. So what we have to do is make a decision. We still need to reduce those 112, and there still may be ways to do that in Quantumol. I'm still working on that also. The other hiccup to this is that it's also very difficult to find cross sections for all the reactions, especially the ion neutral reactions. That can be a challenge also. So for the work I'm going to be presenting here, I've included these 3 ion species, argon plus, CF3 plus, and F plus, I put in one negative ion species, F minus. I put in electrons. And then these are the neutrals I've included. These argon, fluorine, CF4, CF3, CF2, F2, and then these are the excited states I've included. I think most people will recognize that this is getting complex now for a pick code. This is exciting work going forward, being able to even know what to include. And then the VSim has the capability to just put them in and include these reactions. In this work, I needed to choose the reactions. If the ionization threshold was greater than 30 eV, I did not include it. Most of the ionization thresholds are 15 to 20. I also, just as a starting point, I included collisions with the larger densities species because those are going to have a higher probability colliding. And so that's how I figured out which reactions to include. So these are the reactions that I've included in this model. You'll notice these are all reactions with electrons. Part of the reason is because when I started digging into the data, I didn't have the cross sections for those ion-ion collisions or ion neutral collisions. One thing to know here is if you want neutral fluxes onto the wafer, we can do that with our Euler fluid model. This is a simple fluid model which just keeps track of the fluid density, but the Euler model will keep track of the energy, the temperature, and also the flux of the fluid. And without too much addition in the speed of your run times, you can switch over to an Euler fluid model. Okay, just a bit of details on the VSim simulations. I've run these in our using our electrostatic solve. So we only solve for the self-consistent electric field. I'll be modeling a wafer, so we'll be looking at ions impacting the wafer and just the distributions onto the wafer. I've included 2 electrodes on this: an upper electrode at 80 megahertz, I think 100 volts, and then a 100 volt amplitude, and then the lower electrode, which is below the wafer, is 10 megahertz. So this is a 2 frequency CCP type problem that I'm modeling. So here's the boundary conditions. Over on the left, I've modeled in the Poisson solve. I use Neumann boundary conditions, and the particles are reflected. That's on the left and the right. On the top, particles are absorbed, and again, there's that 80 megahertz 100 volt RF source. And then on the bottom, particles are absorbed onto the wafer and the focus ring. And actually, we modeled the accumulated charge on the dielectric, so we can include that effect as well. Okay. So just a brief discussion of the computational scheme. So standard pick is what we would call a momentum conserving scheme. There's no self forces. So this uses the same interpolation scheme to weight the particles onto the grid as the field interpolation back to the particle from the grid. So grid to particle and particle onto the grid, and then interpolation from grid back to the particle is the same interpolation. And VSim has used this for decades. It's very standard in particle and cell codes to use this. However, this does require resolving the electron Debye length. These densities are 10 to the 16, so that's starting to get up there with becoming pretty prohibitive. And so we recently added a new capability, which is an energy conserving scheme, which conserves total energy in the limit that ET goes to 0. And the advantage for this scheme is that we can now maintain numerical stability for grid sizes larger than the Debye length. And so in these simulations, my grid size in both the X and the Y, I would just put dx here, but dx equals dy, which is 2 times the electron Debye length. So that's a nice speed up. It's a factor of 4 speed up. And so these They took about 4 hours on 32 cores. So this is just a plot to show you some of what types of physics that we're wanting to resolve. We want to, of course, resolve this sheath here, which is on the order of 10 to bi length thick, 10 to about 50 to bi lengths, depending on where in the RF cycle you're at. We want to include this physics here, which is, so this is the wafer here. And when it comes to an end, you can get these discontinuities, which lead to problems on how the ions are deposited and how the ions are deposited onto the wafer. And so a common technique is to put this focus ring out on the outer radius right here, and varying the height of that focus ring, varying the dielectric of that focus ring, basically changing the material, is an important thing to model. And so you can see that discontinuity here in the sheath. And then just the discontinuities right here. And then these background dots are just the argon ions. I just superimpose them. And then, so these are the sorts of things that we want to use VSim for, to model these effects, these sheath effects. Oh, sorry, I say a pair of these. White dots are the fluorine or fluoride ions. Okay. Now, I actually wanted to pop out of the presentation and just show you the setup in VSim. Here's what it looks like in VSim. And I just wanted to walk through just a little bit of how we set up the boundary conditions. The whole thing, by the way, is here. Let me rotate it. The radial axis is up and down, and the z-axis is left and right. So that's just so you're aware of that. So this is what it looks like setting up all these species. It's going to take you a little time when you add these, but it's pretty straightforward. So it's nice. And once you're done, you should go take a 15-minute break and rest your eyes and double check, because that's just a workflow issue. When you're doing something tedious, you tend to start making mistakes. But after you put them in, then it only takes about 10 minutes to put them all in. And these are all my neutrals here, so quite a few neutrals. Notice I'm modeling the excited states as neutrals also. And then my reactions here. In particular, I wanted to show you a capability we have in VSim, which is the ability to model an arbitrary number of products and the inputs and outputs of your reaction. So if you right-click here, and you do collision type, and you go down here and you just click on general reaction. Okay, now I have a new general reaction, and I right click on it again, and I can just start adding reactants. And you can add as many reactants as you want, and then same with products. So that's under this particle collision. So and the reason I'm pointing this out is because the reactant in the product can either be a fluid or a particle. So that's just where we happen to put that capability. And this is very important for this problem, because if I go back to the reaction that I've included, up here, you'll notice that this has 2 reactants, but 4 products. This has 4 products also. So we needed to add that flexibility into the GUI, into our GUI framework. And I think that was done in 12.0, but maybe it was done more recently even. So we do have that capability, which has been a part of the Vorpal, but now it's part of the GUI, so it's easier to implement. Okay, I ran the simulation for about 20 or 30 RF periods. And here's a result of the energy distribution of the argon plus, which is yellow, CF3 plus, which is black, and F plus, which is red. And it's clear here that the CF3 distribution is more focused and around a tighter energy. So CF3 behaves differently than the other two ion species. So this is just one result. And then this was averaged over 2 RF periods. Again, if you'll bear with me here, I can show you how we do this in VSim. We actually do that calculation in VSim. If you click on the Analyze tab, and then I use the Compute AED Analyzer, which is right here. And it's a very flexible analyzer, allows you to put in what part of the wafer you want to bin the data. It allows you to put in the time interval. Sorry if it's too small for people, I can't.
I thought you said compute ADD.
Oh, compute AED, compute angular energy distribution. But it allows you to put in whatever time interval you want, whatever spatial region you want, and then you bin the data accordingly. But that is part of our software. Just wanted to point that out. So all these plots were produced in VSim. And here is the angular distribution. And again, colors, the argon is yellow, CF3 is black, and F plus is red. And we see that the CF3 is a bit more narrow than the other two ions. But one of the consequences of adding more collisions in ions is these distributions tend to get spread out more. So it's very important to put in the correct chemistry, because if you're actually going to get the correct angular distributions and energy distributions, you need to be also have modeling the system correctly. And then here is just a plot in a 2D color contour plot of what I just showed you were integrated over angle and energy, but this is the full distribution. And then we could also compute the flux onto the wafer. This is the energy flux. These fluxes scale with the initial density, so we're seeing much larger fluxes of CF3. We see a decent uniformity at the edge of the wafer. Okay, so to conclude, so including complex chemistry in VSim is feasible when you couple it with a global model. The preliminary results indicate the importance of including more realistic chemistries to get the distributions correct onto the wafer. Few initial results are the broadening of the angular distribution due to these collisional processes. And we also see differences in the ion species as well. So CF3 is behaving differently than the other two species. So that's it.
All right, thank you so very much, Daniel. We have a few questions. The first is, what are the exact dimensions of the chamber, and is it electromagnetic or electrostatic?
So the dimensions were, the physical dimensions in reality would go from 0 to 20 centimeters along Z and 0 to 4 centimeters along R. I only included, the simulation went from 5 to 20, so I didn't do the bottom 5 centimeters of the wafer. And these were electrostatic simulations.
Did you account for secondary electron emission?
I did not include that. I have done that in the past, and so I could put that into these simulations. But these results did not include that effect.
We have another question, which is, will this recording of the webinar be available? And yes, they will. It'll take us 1 to 2 weeks, and we will get every presentation that was done today, and they will be on the TechX YouTube channel for you to look at a later date. Another question, do you think CF3 plus is being cooled by the lighter ions?
So we actually, I did not put in any ion collisions. We can do that down the road. So I'm not sure how there would be cooling yet from any coupling of the ions, because I haven't not included that in the model.
Okay. And we'll do one last question before we go on to our last presentation, which is, can resolution of the angular distribution be improved?
Yes, it can be. It's just that noise becomes an issue. So you would probably, if you want better angular resolution, you would probably want more particles per cell so that you're actually populating those angular bends.
All right, thank you so very much, Daniel. Our next presentation is coming up. We are going to take a brief break here. We will start at 11:35 Mountain Time.
Thanks, everyone. Bye.